Materials, equipment, and processes in the manufacture of aluminum, presented to you by Factor, Pesina, Costuna, De Leon, and Padero. Importance of the industry and the contribution to national economy. Aluminum is one of the most commonly used metallic elements. Due to its high corrosion resistance and mechanical strength to mass ratio, aluminum alloys are used as a major structural material in aircrafts, buildings, machinery parts, beverage cans, and food wraps. Aluminum is the most recyclable of all materials. It is 4 times more valuable than any other recyclable consumer materials, and there is no limit to the number of times aluminum can be recycled. The aluminum industry contributes $174 billion to the US economy, close to 1% of GDP. Aluminum is one of the few materials that affect every person in the country, and nearly 700,000 American jobs are supported by the industry. Strong, lightweight, and recyclable, aluminum is a material uniquely suited to meet the needs and challenges of the 21st century. Aluminum is well positioned in the US and global market. More than 166,000 workers are directly employed in the aluminum industry. In total, 659,000 US jobs are supported by the production, processing, and the use of aluminum. Workers in the aluminum industry earn an average yearly compensation exceeding the national average. Indirect employment created by the aluminum industry adds an additional $44 billion in wages and benefits to the economy. Recycling aluminum saves more than 90% of the energy cost required in primary production. The recycling industry is mature and growing. Recycled aluminum cans are worth more than $800 million each year. The aluminum industry pays out more than $800 million for empty aluminum cans. Every minute, an average of 113 aluminum cans is recycled. Aluminum recycling programs have enabled charitable organizations and groups to earn funds to enhance programs and support projects for decades.
The aluminum manufacturing process.
Aluminum is the most abundant metal on Earth. It is not naturally occurring element, but it is usually found in mineral bauxite, which are extracted in bauxite reserves located in Africa, South America, and Oceania. Due to its low density, high thermal conductivity, and corrosion-resistant nature, it has been used in wide applications such as in manufacturing beverage cans, foils, utensils, windows, aircraft, and automotive parts. It can easily be casted, machined, and formed by different fabrication techniques. Since aluminum itself is not particularly strong, it is often used as an alloy and combined with different elements such as copper, manganese, magnesium, silicon, which are lightweight but has great strength. Here are the raw materials used in manufacturing aluminum. Bauxite, which has a chemical formula of Al2H2O4, is a type of sedimentary rock that is composed of aluminum-bearing minerals. It is the main raw material for the aluminum production. It has a melting point of around 1,206 degrees Celsius and usually found in topsoil of tropical or subtropical regions such as Australia, China, Brazil, Malaysia, India, and Guinea. Extraction of aluminum occurs in two processes. First is the Bayer process. In the Bayer process, the bauxite ore undergoes a chemical reaction to produce alumina. The second process is Hall-Herold's process, where the extracted alumina undergoes electrolysis to produce aluminum. The aluminum compounds in the bauxite ore may be present as gibbsite, boehmite, and diaspore. Different forms of aluminum compounds and the presence of impurities dictates the extraction conditions of aluminum. Here is the chemical composition of the bauxite ore. The bauxite ore is primarily composed of alumina, Al2O3 which is 35 to 65%, silica, ferric oxide, titania, and calcium. The caustic soda, or also known as the lye, has the chemical formula of NaOH. It appears as a white, colorless, and clear ionic compound with sodium and hydroxide ions. It is added to the bauxite ore to dissolve the aluminum compounds and purify it from impurities to produce sodium aluminate solution. Alumina, or Al2O3, appears as a white or clear crystalline substance that serves as a raw material for the smelting of aluminum. It has a high melting point of 2015 degrees Celsius and can be extracted as a byproduct from the bauxite ore during Bayer process. Craolite, or Na3AlF6, also called as sodium hexafluoroaluminate, appears as a white or colorless mineral which is used as a solvent during electrolysis of aluminum. It decreases the melting point of the aluminum oxide from 2000 degrees Celsius to 1000 degrees Celsius and increases its conductivity. The craolite is composed of sodium, aluminum, and fluorine and can be extracted through craolite deposits. Synthetically produced craolites are made from fluorspar, or CaF2, which occurs as a natural mineral. The fluorspar is treated with sulfuric acid to produce hydrofluoric acid, which reacts with the sodium oxide and alumina to produce craolite. Carbon or carbon electrodes are used in the smelting process to transmit the electric current through the electrolyte solution. It is consumed during the process and reacts with the oxygen to form carbon dioxide. Here is the process flow diagram of the aluminum manufacturing process. Mining of the bauxite ore. The bauxite ore is usually found near the surface and extracted by open cast mining. The scrapers and bulldozers are used to clear the vegetation sites and collect the valuable topsoil which will be later used for the vegetation. Under the topsoil is 1 meter to 2 meters overburden and is removed by scrapers and small excavators to expose the caprock. Depending on the depth of the caprock, it is usually broken by blasting, drilling, or ripping using bulldozers. The bauxite ore is then mined using excavators. Once extracted, the bauxite ores are loaded to trucks, railroad cars, or conveyor belts, where they are transported to the crusher plants. In the crusher plants, the ores are washed to remove the impurities and are crushed to uniform sizes suitable for transportation. Usually, the size of the bauxite ore is around 7.5 centimeters in diameter or less. Since most alumina refineries are located near the mining sites, the crushed bauxite ore are transported via conveyor belts. However, if the refineries are located far from the site, they are delivered to the shipping terminals where they are transported via ships. There are two processes to extract the aluminum. The first is Bayer process. The bauxite ore are reduced to smaller sizes in the crusher. The caustic soda and lime are added and mixed in the mixer to produce a slurry solution. In the digestion process, the slurry is transferred to the digester tank and heated at 110 degrees Celsius to 270 degrees Celsius at 50 pounds per inches squared pressure. Additional caustic soda may be added to the solution to dissolve the remaining aluminum compounds. The resulting solution here is the sodium aluminate, which is pumped to series of flash tanks to reduce the temperature. In the settling process, the slurry is transferred to the settling tank where undissolved impurities are settled at the bottom. These impurities are composed of sand, iron oxide, and other oxides which are now referred as red mud. The red mud here is washed and recycled and stored in holding pots. The liquor here is filtered to a series of cold filters. In the precipitation process, the seed crystals are added to the filtered liquid as it cools down. Crystals that are added grow and agglomerate to form larger crystals. During the evaporation process, the spent liquor is heated in a series of heat exchangers and cooled in a series of flash tanks. The condensate in the heater is reused, and the excess caustic soda is washed and recycled into the digestion process. In the calcination process, the crystals are classified in two sizes using a series of thickeners such as cyclones or gravity classification tanks. After removing the impurities, the fine crystals are returned to the precipitation process and are used again as seed crystals. The filter cake here is fed into the calciners and are roasted at 1000 degrees Celsius to drive off the moisture and produce aluminum oxide. In the Hall-Heroult process, the pure alumina is added to the molten cryolite and is dissolved at 1000 degrees Celsius, where they are mixed in pots or pot lines. These pot lines are rectangular cells lined with carbon blocks and insulation, which serves as cathode. The anodes are attached to the rods and suspended in the cells, which are used to conduct the electricity to the pots. During electrolysis, the electric current passes through the pots where the chemical reaction occurs. The current flows from the anode to the aluminum and cryolite solution to the cathode and the next pot. The temperature in this process must be maintained to 970 degrees Celsius to 1000 degrees Celsius to split the alumina into molten aluminum and oxygen. The carbon from the anode mixes with the oxygen from the alumina and produces aluminum and carbon dioxide which escapes from the cell. The molten aluminum now settles at the bottom of the pots where it is extracted using crucible. Now, the molten aluminum is transported to the cast house where it is mixed with other metals to form alloys. The molten aluminum is held in the furnace and maintained at temperature of 700 degrees Celsius to prevent it from solidifying. Filtration is done to the molten aluminum to remove its impurities. After filtration, the molten aluminum is poured into mold and cooled and formed into different shapes and cooled by spraying cold water. Aluminum fabrication. In the casting process, the molten aluminum is molded into different shapes. It is used to make solid objects or parts and is applicable for alloys 4XXX and 5XXX series due to their strength and wear resistance. In the rolling process, the aluminum ingots are repeatedly passed by heavy rollers and flattened into thin sheets. Usually, the process takes about 10 to 12 passes to make a tin foil which can be 0.15 millimeters thick. In the extrusion process, the molten aluminum is forced to flow in a die. The shape of the die determines the shape of the extruded aluminum. In the forging process, the aluminum is hammered or pressed under a great pressure to produce a high-strength metal. In the drawing process, the aluminum rods are pulled in a series of smaller dies to produce aluminum wire. And lastly, in the machining process, it uses machine operations such as milling, turning, drilling, tapping, and sewing. This is applicable for alloys 1001, 2001, 3001, and 6001.
To further understand the manufacturing processes of aluminum, here is a short step-by-step video about the manufacturing processes of aluminum.
The raw material from which aluminum is made is found in many tropical areas. Here on the island of Jamaica, the aluminum ore, known as bauxite, lies close to the surface in the rich red earth. It is within easy reach of giant shovels and waiting trucks. To handle the vast quantities of bauxite, a railroad system was built. Harbor facilities were established and a substantial fleet of ore ships contracted for to carry the bauxite to the United States. Refining plants have been built near sea and inland ports to save shipping costs. Here, the bauxite undergoes an intricate chemical process. First, the bauxite is mixed with water, lime, and soda ash. Then it is wet ground, blended with a solution of caustic soda, and transferred to digester tanks. Under steam pressure, the alumina dissolves out of the bauxite, forming sodium aluminate. The impurities remain in solid form, and the sodium aluminate is separated from them in a series of tanks in which the heavier impurities settle. The relatively clear liquid is drawn off the top and piped to filter presses, which remove the finer impurities suspended in the liquid. Then, in 6-story high tanks, the solution of sodium aluminate is agitated by compressed air and seeded with aluminum trihydrate. This encourages the formation of aluminum hydroxide crystals, which precipitate to the bottom of the tanks. Next, the crystals are thoroughly washed and heated to 2,000-degree temperatures in long rotary kilns. This drives off the free and combined water, and the result is a white powder, aluminum oxide, known as alumina. The alumina is shipped in trainload lots to Kaiser Aluminum's reduction plants for processing to metallic aluminum. The reduction process requires vast amounts of electrical energy that can come from hydroelectric power, from using coal, or by using natural gas as a fuel source. But regardless of the power source of electrical energy, the reduction process is the same. The alumina is put into an electrolytic bath of molten cryolite into which a carbon electrode is suspended. A molecule of alumina is made up of 3 atoms of oxygen holding fast to 2 atoms of metallic aluminum. Electrical energy frees the aluminum atoms from the oxygen atoms, and the molten aluminum sinks to the bottom of the bath. Periodically, the molten aluminum is siphoned from the pots, placed in holding furnaces, and poured into ingots. This primary aluminum, in the form of ingots, is shipped to customers either in pure or alloyed form. The fabricating process begins with alloyed blooms, which, after being reheated, are passed through the rolling mills. The blooms are subjected to millions of pounds of pressure to decrease their size and alter the molecular structure of the metal to increase its strength and durability. In the manufacture of wire, ingots of workable length are processed in the continuous rod mill. The fully automatic process is completed by a series of reductions. For customers who need wire of smaller size, the rod is fed into machines and pulled through a series of dies of decreasing diameter, which lengthen and reduce the metal by drawing until the desired size is obtained. In addition, the plant makes many specialized types of wire and cable products, including aluminum cable steel reinforced for high tension lines, known as ACSR, and all aluminum cable, known as AAC. Triplex Service Drop combines 2 polyethylene-covered wires wound about a bare ground line, filling the need for a lower cost, simpler to install link between power lines in the nation's homes and buildings. At modern extrusion plants, like this one located near Baltimore, Maryland, designs and shapes like these are extruded through dies. Experienced designers are available to customers to make dies that meet the most exacting specifications. The die makers know from long experience that the most careful execution of design is essential to properly control the flow of metal through the die. The extrusion process begins with billets, specially alloyed and cast for the specific need. Pressure exerted by the extrusion press squeezes the workable metal through the die like toothpaste. In this case, forming an I-beam for a truck trailer chassis in one simple operation. The workability of aluminum and the simplicity of the extrusion process make possible almost numberless designs, including window frames, decorative molding, furniture tubing, storefronts, structural members for transportation equipment and buildings. Huge ingots are subjected to tremendous pressures in the rolling process. Driven by thousands of horsepower, the rolls compress the ingot, and after several passes, it is reduced from its original thickness of 13 inches to 3 inches, and its length is increased from 9 to 30 feet. As the rolling process continues, the slab is reduced from 3 inches down to 7/8 of an inch in thickness, and its length is increased from 30 to 125 feet. The slab then moves into a huge 5-stand continuous mill. Actually, it is 5 mills working in tandem to reduce the 7/8 inch slab down to sheets of 1/10 of an inch in a single pass. Observing this tremendous mill in action, one can't help but sense that here in this massive complexity is a symbol of the strength of the American private enterprise system. Operated by highly skilled workers, the costly equipment is made possible through investment by thousands of stockholders, men and women who believe that our American economic system can continue to produce more things for more people efficiently and without waste. The sheet streams out of the 5-stand mill and onto the roll-up machine, where it is coiled at high tension into large, tight rolls ready for further processing. Some sheet is cut into circular sections to make washing machine tubs. Blanks are stamped from aluminum sheet to make products like pots and pans. Some sheet may be slit into workable widths for fabricators of heat exchangers or refrigerator trays and liners. Some coil sheet is further processed at foil mills in West Virginia and California. Here it is rolled into foil of various gauges for packaging, building insulation, and electronic components. Whether it's foil for decorative purposes or flat sheets for the fuselages of jet planes, close inspection and quality control are observed in every plant over every process. For example, a flying micrometer keeps sheet gauge within the most minute of tolerances. Ultrasonic waves scan heavy plate and billets for internal flaws. Should any exist, they are revealed on the electronic screen. And the alloy content of the metal itself is analyzed by direct reading spectrograph, called a quantometer. These quality control procedures help sustain the high standards which fabricators and the public have always associated with aluminum products. Kaiser Aluminum works constantly with fabricators to solve technical problems and to develop new and better uses for aluminum, such as this tank to contain liquid hydrogen at minus 423 degrees Fahrenheit, which takes full advantage of aluminum's light weight, weldability, and increased strength under extreme cold. Agriculture has already benefited from new aluminum products. Rolling stock made of this light, durable metal helps railroads to increase payloads and cut maintenance costs. In the construction industry, glass fiber wall panels sandwiched between two sheets of aluminum give 3 times the insulation of 8 inches of masonry. Lightweight, strong, corrosion-resistant culverts are an example of aluminum's contribution to modern highway construction. Aluminum engine blocks are being used in the automotive industry, as well as an aluminum wheel and brake drum cast in one piece. Not only will aluminum continue to improve and replace existing components in the automobile industry, it is certain to find more uses in all our daily lives.
Hi there, I will be presenting the problems in aluminum production. First off is its energy consumption. So to compare its consumption, for 1 ton of aluminum, the plant uses about 211 gigajoules of power. Meanwhile, for 1 ton of steel, the plant would only require about 22.7 gigajoules of energy. So in this one, as long as the world gets creative on harvesting energy or electricity, the consumption on aluminum industry will also continue to improve. Next one is the anodizing waste. As we anodize the aluminum, PNH and VOC are being emitted throughout the formula, VOC emissions being minimal. So PAH stands for polycyclic aromatic hydrocarbon, while VOC is volatile organic compounds. So to make this useful, anodizing waste are being used in water treatment facilities to fasten the water treatment process, or the solidification of the dirt in the water. Also, anodizing efficiencies are still on the studies for improvement so that they can lessen the emissions. Lastly is our aluminum waste. Aluminum waste like can, container, or something like an old cooking tool. So recycling aluminum waste is the most common solution for this. And recycling aluminum saves about 90% of the energy and reduces its emission by 8%. In other countries such as America, Australia, and Korea, they put strict rules on segregating aluminum waste for them to be recycled. They also put landfill bans on aluminum cans and container, not only for recycling, but also for the safety of the landfill workers.
Assessment of the safety and health practices. There are 2 types of indicators must to consider having in health and safety issues: the lagging indicators and the leading indicators. The lagging indicator are also known as the trailing, downstream, or after the fact indicator. It provides historical information about healthy and safety performance. With this indicator, nothing can be changed to alter the measure of health and safety performance, as it is history. Any changes made may influence future performance, but as it cannot alter the past performance. While the leading indicator, or also known as upstream indicator, are used as predictors of health and safety performance. The advantage of using this indicator is that action can be taken to alter the course of health and safety performance. In case of predicted poor performance, it is not necessary to wait the test if the prediction is correct. It can be changed and implemented already to increase the probability of improved performance. Thus, this indicator can provide guidance where there is greater assurance of achieving good health and safety performance rather than waiting for accidents to happen. Here are the summary of hazards while working with aluminum. Aluminum can easily affect you when breathed in. Contact with aluminum can irritate the skin and eyes. Exposure to aluminum can cause metal fume fever. This is a flu-like illness with symptoms of metallic taste in the mouth, headache, fever and chills, chest tightness, and cough. These symptoms may be delayed for several hours after exposure and usually last for a day or two. Exposure to fine dust can cause scarring of the lungs or the pulmonary fibrosis, with symptoms of cough and shortness of breath. The aluminum powder is a flammable solid and a dangerous fire hazard. Here are some ways of reducing exposure to aluminum. If possible, use enclosed operations and local exhaust ventilation at the site of chemical release. If local exhaust ventilation or enclosure is not used, respirators should be worn. Wear protective equipment for clothing. Wash thoroughly immediately after the exposure to aluminum. Post hazard and warning information in the work area. In addition, as part of an ongoing education and training effort, communicate all information on the health and safety hazards of aluminum to the potentially exposed workers. Here are the workplace exposure limits to aluminum. According to OSHA, the Occupational Safety and Health Administration, the legal airborne permissible exposure limit or PEL is 15 mg per cubic meter for total dust and 5 mg per cubic meter for respirable dust average for over an 8-hour period of work shift. While according to NIOSH or the National Institute for Occupational Safety and Health, the recommended airborne limit is 10 mg per cubic meter for total dust and 5 mg per cubic meter for respirable dust average for over a 10-hour period of work shift. Lastly, according to ACGIH or the American Conference of Governmental Industrial Hygienists, the recommended airborne exposure limit is 10 mg per cubic meter for total dust and 5 mg per cubic meter for pyro powders average for over an 8-hour period of work shift. Here are the health hazard information. There are two effects to consider while working with aluminum. The acute health effects. These acute or the short-term health effects may occur immediately or shortly after exposure to aluminum. The example of this is the metal fume fever. As I said a while ago, this is a flu-like illness with symptoms of metallic taste in the mouth, headache, fever and chills, chest tightness, and cough. These symptoms may be delayed for several hours after exposure and usually last for a day or two. The other one is the chronic health effects, or the long-term health effects can occur at the same time after exposure to aluminum and can last for months or years. The example of this is the cancer hazard. While aluminum and aluminum compounds have not been identified as carcinogens, aluminum production has been determined to be a human carcinogen. The second one is the reproductive hazard. Nowadays, the aluminum tested has not been shown to affect reproduction in humans, according to a present study of the New Jersey Department of Health and Senior Services. The last one is the other long-term effects. Pulmonary fibrosis is the example of this. because this is due to the exposure to fine dust and having symptoms of cough and shortness of breath. Here are some medical ways to consider before working with aluminum. Medical testing. Before beginning employment and at the regular times after that, or at least annually, must have the following tests to evaluate the history of the past health and present symptoms found in the exam. Lung function test and the chest X-ray after acute overexposure. The other one is the mixed exposures. For person who smoke that can cause heart disease, have lung cancer, and other respiratory problem, it must stop or end working to reduce the risk of developing more health problems as it may worsen the respiratory conditions caused by the chemical exposure to aluminum. Here are some workplace controls and practices must to consider. The engineering controls. This is the most effective way of reducing exposure. The enclosed operation provide local exhaust ventilation at the site of chemical release is the best protection anyone can get because isolating operations can reduce exposure. The use of respirators and protective equipment is less effective than the controls mentioned, but it is sometimes necessary. In evaluating the controls present in workplace, consider the following: how hazardous the substance is, how much of the substance is released into the workplace, whether it is harmful when skin or eye contact could occur because special controls should be in place for highly toxic chemicals or when significant exposures are possible. Work practices. The following good work practices can help to reduce hazardous exposure while working with aluminum. Workers whose clothing has been contaminated by aluminum should change it to clean clothing promptly, but do not take the contaminated work clothes to home as per the family members could also be exposed. The contaminated work clothes should be laundered by individuals who've been informed the hazards of exposure to aluminum. It must have eye wash fountain provided in the immediate work area for emergency use. If there is possibility of skin exposure, emergency shower facilities should be provided. Immediately wash or shower when on skin contact with aluminum to remove the chemical. Use a vacuum cleaner to reduce dust during cleanup and do not dry sweep. For personal protective equipment. Workplace controls are way better than personal protective equipment. However, for some jobs, the use of personal protective equipment may be appropriate, such as outside work, confined space entry, or jobs done while workplace controls are being installed. Here are some guidelines to consider but may not apply to every situation. The clothing. All protective clothing, such as suits, gloves, footwear, or headgear should be clean, available each day, and put on before work to avoid skin contact with aluminum. The safety equipment suppliers or manufacturers can provide recommendations on the most appropriate protective clothing material for operation. For eye protection. Always wear eye protection such as side shields or face shields along with the goggles when working with corrosive materials, highly irritating or toxic substances. For the safety, handling, and storage of aluminum. Prior to working with aluminum in powder or granular forms that reacts violently with water should be handled and stored properly. Aluminum is not compatible with strong acids, oxidizing agents, acid chlorides, strong bases, fluorinated hydrocarbons, and alcohols. It must store in tightly closed containers in a cool, well-ventilated area away from the moisture and must protect the containers against physical damage. Sources of ignition, such as smoking and open flames, are prohibited where aluminum powder is used, handled, or stored. For metal containers involving the transfer of aluminum powder, it should be grounded and bonded. Wherever aluminum powder is used, handled, manufactured or stored, use non-sparking tools and equipment, and explosion-proof electrical equipment and fittings. Store the aluminum powder under nitrogen.
Environmental impact assessment. Emission and environmental effect. Aluminum is heated in an ore called bauxite. It's a red dirt and clay mixture commonly found in Australia, Brazil, and India. If you're looking for shining bits of silver in the ground though, you won't find it. Aluminum, as we know, it has gone through a lot to get to our supermarket shelves. Bauxite is collected from the ground in an open pit mining operation. It doesn't sit very deeply in the earth crust, so some energy can be saved on drilling. However, to recover all the aluminum in an area, swathes of land must be bulldozed to reveal to the dirt and an ore underneath. As you probably noticed, turning bauxite into aluminum requires a lot of energy and has a variety of environmental impacts. Both open and underground mines affect the plant and animals' life immediately, surrounding an area and beyond for multiple generations. Clear-cutting trees and the grassland contributes to the biodiversity loss, habitat loss, carbon emission, and erosion. Mining operations have taken this damage into account and more in recent years, incorporating plants to restore the grow natural habitats once mining is complete. All refining process use varying levels of electricity and water, which can cause higher carbon emission, create air and water pollution, and even do noise and heat pollution. Methods to contain the effect. Recycling. Recycling aluminum is a sustainable metal and can be recycled over and over again. An aluminum can generally turn into a new can and back on store shelves within 60 days. Cans are usually available through the curbside pickup or a community drop-off location nationwide. There are many advantages of recycling aluminum, since it takes more energy to dig up and produce aluminum than any other metal. Recycling not only avoids the extraction of the earth, it also saves energy, lots of energy. Recycled aluminum requires 90% of less energy than producing new aluminum and generates only 5% of the greenhouse gas emission. 75% of aluminum produced in history is still used. The recycling of aluminum can save enough energy to power more than 4.4 million European homes for an entire year. If all cans were recycled, this figure could be 6.4 million homes. A total of 125 billion aluminum cans are recycled every year. This is enough to build more than 80,000 Boeing 737 planes every year, over 10 times the total of 737 ever built. A billion tons of recycled aluminum is still in use today. Thank you.